Hello, welcome back to the channel. We continue to review the principles and practices of commercial construction textbook, and this video is dedicated to chapter 5, and this chapter is about foundations. So let's dive deeper into this sub chapter here that is called Need for Deep Foundations. So the foundation of a building is generally regarded as that part of the structure that transmits the superimposed load of the building to the supporting soil. And the foundation must be proportioned to ensure that the superimposed building loads do not exceed the load-bearing capacity of the soil, and that differential settlements are kept to a minimum. So normally soils near the surface are less stable and less densely compacted than the material some distance below the surface. So by removing the upper layer of unstable soil, the building weight is distributed evenly and can be supported by more densely compacted material that has been exposed. A foundation that is relatively short distance below finished grade is termed a shallow foundation. Shallow foundations are usually made of cast-in-place reinforced concrete and consist of isolated pad footings to support column loads, continuous strip footings under load-bearing walls, or a variation of the two to ensure the proper distribution of loads. However, the term is relative as there is no hard rule for determining when a shallow foundation becomes a deep foundation. One special type of foundation known as mat foundation can be characterized as either a shallow foundation or a deep foundation, depending on its placement. For large buildings to develop adequate support for the imposed loads, it's not uncommon for portions of their foundations to extend to bedrock or to a depth sufficient to achieve load resistant capacity through a combination of skin friction and end bearing, particularly when bedrock is too deep below the surface on the bedrock or the bedrock is not consistent or competent. This type of foundation can be termed a deep foundation and is accomplished through the use of piles, caissons, deep wall foundations, mats, and in some cases, a combination of mats and piles. So please always refer back to the textbook. Just back up the videos with the diagrams and some graphical representation that you can find there. And we are moving to the next subchapter, that is types of piles. So there are generally four methods or means to use to install piles. And these methods include driving the piles with a pile driver, jetting the pile using water jets, drilling and pumping concrete, and vibrating the pile in place. So wood, steel, and precast concrete sections are driven. Concrete piles and caissons are placed into pre-drill shafts that may or may not be lined with steel casings. Concrete piles are drilled using a hollow stem auger through which concrete is pumped as it's extracted. The type of pile placement is usually determined by the soil conditions and the magnitude of the loads that must be supported. So when considering load transfer characteristics, there are four variations: bearing piles, friction plus bearing, and sheet piles. So let's take a look at the parts of a typical pile, and those are head, and that's the upper part in final position, then foot, the lower part, tip, the small end before or after it's placed in position, then butt, the large end before or after it's placed in position, pile ring, a wrought iron or steel hoop that is placed on the head of the pile to prevent cracking, brooming, or splitting. Driving head, that's a device placed on the head of a pile to receive hammer blows and to protect it from injury while it's being driven. A driving head may be used instead of a pile ring. And then pile cut off, and that is the portion of the pile that is removed after completion of driving, and the pile shoe, and that is the metal cone placed on the tip of a pile to protect it from cracking or splitting. So you can see there is the diagram showing the section. So, and we are moving to the next little subchapter, and that's the bearing capacity of pile foundations. So the design of pile foundations consists of two general steps. The first one is the selection and design of the piles and the driving equipment to be used. And the second one is the study of the soils to which the loads are transmitted. So again, please refer back to the textbook. There is an example of a problem with the solution. So you need to be familiar with the way those problems are solved and the calculations are done. So pile caps, piles supporting gravity loads can be used individually or in groups. So a pile cap is a cast-in-place reinforced concrete pad or sufficient thickness placed over the top of the pile group so that the supported load is shared by each supporting pile. Again, please refer to the diagrams. You can see here the typical dimensions of a pile cap supporting a concrete column and then other things. So please make sure that you see those images. And excuse me, we're moving to the wood piles. So considerable selection is necessary to obtain good wooden piles. So they must be free from large or loose knots, decay, splits, and shakes. Crooks and bends should be no more than 1/2 of the pile diameter at the middle of the bend. And pile sweep should be limited so that um, piles less than 70 feet in length, a straight line joining the midpoint of the butt and the mid joint of the tip does not pass through the surface of the pile. And for piles between 70 to 80 feet in length, a similar straight line does not lie more than 1 inch outside the surface of the pile. And then for piles more than 80 feet in length, a similar straight line does not lie more than 2 inches outside the surface of the pile. So those are some considerations that we need to take a look at. So there are some advantages of using wood piles. Those are as follows. Wood piles have an indefinite life expectancy when placed underwater or driven below groundwater level. Then wood piles are light. In many areas, wood piles are readily available, relatively inexpensive, and easy to transport. And then the last one, wood piles produce greater skin friction than piles of most other materials. So when we talk about concrete piles, there are a few things that we need to remember, and there are two principal types of concrete piles: cast in place and precast. So you know the difference that cast in place is formed in the ground in the position in which it is to be used, and precast is usually cast in a factory where pre-stressing techniques can be employed, and after curing, it is driven or jetted like a wood pile. So cast in place piles are divided into two general groups, and those are shell type and shell-less type. So shell type are made by first driving a steel shell or casting into the ground, filling it with concrete and leaving the shell in place. And also such piles may or may not be reinforced depending on circumstances. And there is a number of shell type piles that are made. You can take a look at the diagrams here, how that is developed. So it can be a cased pile with compressed base, then it can be a button bottom cased concrete pile, then cased pedestal concrete pile, and so on. So shell-less piles are made by driving a steel pipe fitted with a special end or tapered shoe into the ground for the full depth of the pile. The pipe is then pulled up, leaving the shoe at the bottom, and the hole is filled with concrete. This type of pile is satisfactory where soil is cohesive enough so that a reasonable smooth inside surface is maintained when the shell is removed. And again, please refer to the images. You can see some variations here, and you can see how actually that is drilled, and you can see the casing for pile. So, and you can see how the reinforcing cage for pile is used, and baling equipment for pile bottoms. So how that is used in the earthwork. So, and we are moving to the precast pile shapes. So those and precast piles in general. So the precast concrete piles are normally made in a casting yard under controlled conditions. This allows not only the development of high-strength concrete, but also flexibility in design, reinforcing length, and so on. So they are made in round, square, hexagonal, and octagonal shapes, and you can see different variations of that here. There is there are some diagrams here. So we are moving to the steel piles. That's the next subsection of this chapter. And a steel pile may be a rolled H section or a steel pipe shown as a tubular or pipe pile. And you can see there are pictures here. You can see the air hammer driven steel HP shaped piles into the ground. So the possibility of the pile tip striking a large boulder below the surface is the actually one point that should be considered. So there have been many instances in which long steel piling have been deflected by massive boulders below the surface. And as a result of continuing driving, the pile tip has worked itself to the surface of the ground again. So that's why the investigation needs to be made before actually driving the piles into the ground. Again, refer to the images. You can see the hollow pipe sections with H sections welded to the ends for use as piles. And we are moving to the composite piles. So two materials may sometimes be combined to make up a single pile. The most common combination is wood and concrete, and the result is known as a composite pile. So the wooden pile is driven to ground level, and the head of the pile is fitted with a steel casing. Driving continues, excuse me, by means of a mandrel or core until the required depth is reached. The mandrel is then withdrawn and the shell filled with concrete. So please take a look at the pictures here. You can see what actually needs special consideration, and you can definitely take a look at how it is done in sections. So we are moving to the pile drivers section. It is a very brief section, just we need to understand how that is done. And pile drivers may consist of a drop, mechanical, or vibratory hammer. So a drop hammer is the simplest type of machine consisting of a heavy weight lifted by a cable and guided by leads, which is allowed to drop freely on the pile head. The hammer of a mechanical driver operates like a piston actuated by steam, compressed air, or the internal combustion of diesel fuel. And you can see there are a few variations here. And the vibratory hammer is secured to the head of a pile and operates by delivering vibrations to the pile head in up and down cycles in varying rates of up to about 100 CPS. So the assistance may have to be provided when piles are being driven. This is particularly true when driving precast piles in granular soils. The high friction rate makes driving very difficult, and the assistance is usually in the form of a water jet that dilates the soil at the pile tip. Water is jetted down the hollow center and returns to the surface around the outside of the pile. And please take a look at some of the illustrations here in the textbook. And we are moving to the caissons. So the increase in column loads in many modern buildings due to the wider spacing of columns in order to get more uninterrupted floor space, and in some cases the depth required to reach good bearing strata, has made pile groups impractical in these situations. So in their place, many designers use caissons. So caisson is a shell or a box or casing that when filled with concrete will form a structure similar to a cast in place pile, but it is larger in diameter. So over the years, the term has come to mean the complete bearing unit. So bored caissons, what is that? The development of boring tools for large diameter holes and the equipment to handle them has made the use of bored caissons much more common. So that is the caisson in which a hole of the proper size is bored to depth, and then the cylindrical casing or caisson is usually set into the hole. The use of heavy equipment has made it possible to bore 10 feet diameter holes to a depth of over 150 feet. So you can take a look at that, how that is done. And then there are other types such as jacked in caissons. So, and that is used in the materials such as silt, wet sand, or gravel, which present difficulties in installing bore caissons. So, in that case, a caisson may be forced into the ground by jacks, while at the same time it is rotated back and forth to reduce the side friction. Then we move to the Gao caissons, and they are made in tapered sections, each of which each of the sections fits inside the one above it. So a pit is dug and the first section of steel casing is placed in it. Then it's forced into the ground by driving and excavating inside the cylinder at the same time. And a cylinder 2-inch smaller in diameter is then placed inside the first and driven to its full depth. So this continues until the full depth of the casing is reached. So you can see there are sections of that. And then there are drilled in caissons. And this is where loads to be carried are very large and the depth to bearing rock is excessive, or the type of material encountered is unsuitable for bore caissons. So this is when the drilled in caissons can be used. So when the bedrock is reached, a socket that is slightly smaller in diameter than the caisson shell is drilled into the rock, and HP shaped heavy steel or the equivalent is reinforcing rods and is installed to extend from the top of the caisson to the bottom of the socket. And the last variation is the slurry caisson or drilled shaft. So the technique of using slurry walls can also be applied to the construction of deep piers, shafts, or caissons. And a hole, how it's done, so a hole from 36 inches to about 96 inches in diameter is drilled into the soil while a bentonite slurry is pumped into the hole to keep the sides of the excavation from collapsing. The shaft is then filled with concrete, displacing the slurry and forming a concrete shaft. And this is an example of like a wet method drilled shaft. This method can also be done dry, and that totally depends on the soil conditions. So let's take a look at the cofferdams. So cofferdam is a temporary box-like structure used to hold back water or earth while work is being done inside it, and then it is removed. So just another terminology here. We are moving to the spread foundations. So spread foundations may be isolated to support concentrated loads from columns or strip footings under walls, or they can be designed as one large monolithic pad under the entire building area. So when unusual framing requirements in the building must be supported, or if non-uniform soil-bearing characteristics are encountered at the site, piles can be used in conjunction with the pad. So there are a number of variations for spread footings, and the one that will be used in any particular case depends on the soil conditions and load concentration. So that totally depends and varies from site to site. Um, Foundation placed as monolithic pads are commonly known as mat foundations. And you can see there are pictures showing the preparation for the mat foundation and reinforcement here. Also, what else is important here? So when existing footings must be underpinned or increased in size, grillage footings can be used effectively for the distribution of building loads by providing additional bearing area. Please take a look at the diagrams here. And we are moving to slurry wall foundations. So they may be used as foundation walls as well as protection of an excavation during the excavation stage. So if the wall is to be used as part of the foundation, its thickness will have to be designed accordingly, but otherwise the procedure is the same as for the excavation, for an excavation slurry wall. We are moving to the earthquake resistant foundations. So the damage from an earthquake usually occurs in two stages. The initial damage to the building frame due to the shock waves of the earthquake, and the secondary effects such as fire and flooding due to the damage incurred by the service lines to the building. So major loss of life occurs when collapse of a building is sudden and progressive. So um, the shock waves produced during an earthquake can have a detrimental effect on soil-bearing properties to the extent that a fine-grained soil will liquefy and lose its bearing strength. Although building foundations can be designed to accommodate changes in soil properties, the effects of the resulting horizontal forces transmitted to the superstructure must also be considered. Please again refer to the diagrams here, and there's one showing the horizontal force in building columns due to earthquake action, how that actually moves side to side, the horizontal shear forces. So there are seismic isolator pads for building columns. So that can minimize the damage from the secondary effects of earthquake forces. Also, computer programs provide the structural engineers the means to model and analyze entire structure with various load and scenarios, allowing for better designs and use of structural materials. So that can be done in advance, and that can save time and money. And we are moving to the last subsection of this chapter, and that's soil enhancement for foundations. So the deep foundation systems described here that we discussed are based on techniques that rely on soils that are relatively stable and have the strength characteristics necessary to support superimposed loads. The traditional approach to foundation construction requires drilling or excavating to a depth where bedrock can be reached as the barren stratum, or where naturally consolidated soils have been the required bearing strength and stability. So in areas where good soil characteristics may be lacking, these traditional methods may be too expensive or time consuming. So an alternative to the traditional approach for the construction of building foundations in areas with poor soil is that of soil enhancement. It's also known as soil modification, and it's used to improve the bearing capacity, shear strength, and the settlement characteristics of the soil rather than removing it or passing through it with the foundation. So materials that may be used for soil enhancement include soil, clean gravel, cementitious grout, chemical grout, and injected polymer foams. So, and you can see there are different standards, and it's usually good to follow those recommendations from the lab test and the modified Proctor test, and then just design accordingly. Mini piles, let's take a look at that. So that is the innovation in foundation construction, and it's used in conjunction with soil enhancement. So it's the mini pile or a micro pile is a smaller diameter pile that has been developed for foundation upgrades under existing structures where access and headroom are limited. Then vibroflotation foundation that works best in sandy soils, and it employs mechanical vibration of soil beneath the surface and simultaneous saturation with water to move, shake, and float the soil particles into a dense state. You can see there is a machine showing, and there's like a whole process how to do that, and you can see the vibrator with water jet on, how that works. And you can see that inserted in soil, how that works in section. So please review those images, and that will be helpful for you understanding how that works. So vibro replacement process. During that process, the soil is first displaced by the vibrator. If there is a high moisture content, holes are excavated by a drilling bucket or other suitable means. And the holes are backfilled in stages with coarse material, which is simultaneously compacted by the vibrator. And the last little chapter here is vibratory probe soil compaction. So during this process, a tubular probe is driven into the soil by means of a vibratory driver, similar to the vibro placement process, and then extracted again by the same means. So this causes the soil particles to readjust themselves into a denser state. So, and this actually wraps up our chapter 5. Thank you so much for watching. I will see you in chapter 6.